Problem 10 is in the force body diagram problem, free body diagram problem. Pretty simple. So we have a pulley with two blocks on it, and we're looking for the acceleration of block 3. It's worth noting the acceleration of both blocks should be the same because it is an attached system. So you'll just be looking for the acceleration of the system, and that is the acceleration of a 3 kilogram block. A few assumptions that we've made: the rope is massless, makes all of our math simpler, and the pulley is frictionless, and that means we're not going to lose any energy as the rope's going around the pulley. So I have drew two free body diagrams. They're really simple. Over here we have the 5 kilogram block. It has a force pulling it downwards of mass of the block times acceleration due to gravity, and then it has tension pulling it up. Block 3 has the same tension pulling it up, and it has the same acceleration due to gravity pulling its 3 kilogram mass downward. We can also assume that both tensions equal each other. That's the definition of tension around a pulley. As long as the rope's not broken, stretching, or slipping or anything like that, the tension is equal on both sides of the pulley. So next we're just going to do our Newton's second law equations. So this is for block 3 kilogram block. Our force. Last thing I want to mention is I've defined the system's positive motion to be up on the right side and down on the left side. So that means I will call positive direction down for the 5 kilogram, just because that means all of our positive and negatives will line up as long as the system is moving in one coordinate system, essentially. It doesn't make sense down being positive, but the system should have one singular direction, if that makes sense. So our sum of forces for block 3 is going to be equal to mass of block 3 times the acceleration, again, of the system. That equals the positive force is going to be tension if we're going upwards, minus the negative force of the force pulling it back, which is the force due to gravity, so m3 times g. And then we can just go ahead, I'm going to solve for tension because that's what I'm going to use to substitute later. So tension equals mass 3 acceleration plus the acceleration due to gravity. In our block 5 kilogram block system, the sum of our forces is going to be mass 5 times the acceleration of the system equals, in this case, gravity is our positive or forward moving force, so it'll be m5g minus tension. I'm just going to go ahead and plug the tension we found from the first block 3 equation and plug it right into this one. So we're looking for m5a equals m5g minus m3a plus g. We're looking for a because the acceleration, again, is the same acceleration for both blocks. So I'm going to multiply this side out, factor it out, and then bring like accelerations to the one side of the equation. So I have m5a plus m3a equals m5g minus m3g. So I can pull out my a, and I'm going to get m5 plus m3, or the total mass of the system, and that's going to equal the gravity, acceleration due to gravity, times block 5's mass minus block 3's mass. And that means our acceleration is going to equal the acceleration due to gravity times this fraction. And if you say just pick numbers, say 5 and 3 for these masses, again, this is a made-up step. Actually, I'm sorry, it's not a made-up step. We know these masses, so if we just solve for this, it's going to be 5 minus 3 over 8, and that is going to equal 2 over 8, or g over 4. So our acceleration is 1/4 the acceleration due to gravity. If you assume acceleration due to gravity is 10 meters per second, we're going to get 5 over 2 meters per second squared. Usually you could throw a negative sign on there, but again, I've defined the positive direction to be down in the situation, so I'm going to leave it as a positive number. Now, if you want to check this and see if it makes sense, you have a fraction of gravity to be your acceleration of the system, and that does hold up because something is holding your block back. So if you just drop the 5 kilogram block downwards, it would move in the acceleration of g, no matter what. But you've now attached a mass over a pulley, basically pulling it upwards some fraction of its own, to some degree, so it has to slow it down in some capacity. Therefore, you have a fraction of gravity, acceleration due to gravity. And that's it. Okay, another free body diagram problem. This case situation, we have mass 1 on a surface, and then at mass 2 is free hanging, and there's a pulley holding them together. So we know, or we're going to assume massless rope like usual. We're going to assume frictionless pulley like usual. Those should never change. That math is beyond what they want you to understand. And then we're going to assume frictionless surface that M1 is on. And then they ask us later to not assume that. We're going to have to, analyze what we're doing differently. But we can talk about that in a second. So another thing that we know is that T1 is going to equal T2. Again, that is always the assumption, assuming the rope is not breaking, stretching, or any other weird thing like that, and that is a safe assumption. Next, I'm going to say the positive motion of this system is going over the edge and down, and I'm going to hold that true for both of my blocks here when I do their free body diagrams. All right, starting with 1. We're going to have 2 forces up and down, 1 being the normal force, and then 2 being the force due to gravity, which is equal to mass 1 times the acceleration due to gravity. The only other force we have in the system is tension, which I'm just going to write right here. And then in orange, I'm going to add a second force, the force due to friction. But that doesn't exist right now because we're assuming there's no friction for now. This is MEM1, or I'll just call this block 1. Block 2 is much simpler. It has the force due to gravity, which equals M2 times gravity, acceleration due to gravity, and then times tension. So from this point on, we're just going to go ahead and do our normal equations. So for block 1, the sum of our forces equal mass of 1 times the acceleration of the system, equaling to just tension. That's because tension is the only force pulling in the x direction. I guess we should annotate that this is 1 in the x direction. 1 in the y direction, which we won't really use, sum of all forces, positive is going to be the force, the normal force minus the force due to gravity, and that just equals 0. Some problems that could be irrelevant. Right here, it's not going to be any part of our situation. It's 0 because the block's not coming off the surface or pushing into the surface. There's no acceleration. Our second system, and I'm going to call this the x direction as well, assuming that this is all one plane. It doesn't really intuitively make sense for me to call this up and down vertical right here in x direction, but if it's the same motion as this left right x direction, I'm just going to keep my annotations similar. So our sum of forces here, positive direction is going to be the force due to gravity minus tension holding it back from moving in our positive direction, and that is going to equal M2 acceleration of the system. So if we want to go ahead and we're solving for, what are we solving for? First, we're solving for tension. So in acceleration, let's start with acceleration. So if we plug this equation right here into this equation, because our tensions are the same, we're going to have M2A equals M2G M2A times M2G minus M1A, where this FG is M2G. And if we solve for acceleration, we're going to bring this to the left side, and we're going to have M2 plus M1. We're going to get that usual total mass value, and that equals M2 over G. And we're going to get acceleration equals M2 over M2 plus M1 times G. And again, this makes sense because that is going to be some fraction of the acceleration due to gravity. And just like our previous problem, it makes sense that this isn't free falling with the acceleration due to gravity because something right here is holding it back. All right. Now, if we want to just solve for tension, we can go back and plug in if we want. Tension equals, in this equation right here, M1 times acceleration. So if we just have acceleration, it's going to be M1 times acceleration. We're just going to get M1 times M2 over M2 plus M1 times G. And this is our tension force.